Hey everyone, and welcome to our final video in Unit 3, Applications of the Derivative. Our final application is a topic called differentials, and that's what we're going to study today. And as you can see, I just have the notes right here set up, and we're going to do one example, and then on the back of this sheet is your mastery. We're going to start in slow here today with differentials, so I just have 3 mastery problems for you. Okay, so let's take a look here at what differentials is. First off, I think it's a good idea to look at the first example. Take a look at this. It says, find a good approximation for the square root of 4.6 without, I think that's the key word there, without the use of a calculator. So right now, if I ask you to approximate the square root of 4.6, I mean, I'm not saying you couldn't do it. It would take you some trial and error, multiplying different numbers times themselves, and trying to get close to 4.6. But what if I told you that calculus allows you to get a really, really, really good approximation to this really, really, really quickly without trial and error? That's what differentials are all about. So we're going to take a look at this graph that I've laid out for you here. And as you can see, this graph looks familiar. It's the exact same graph we derived the derivative formula for back in Unit 2. If you remember, we had the PQ graph. So we already have this graph here with P. And what I'd like you to do is we're going to give P some generic coordinates, kind of like we did back in Unit 2. We're going to call this value, this X value, we're just going to go ahead and be really creative, and we're going to call it X. And then the Y value that goes with P, we'll just call that function of X, f of X. And what that does is that gives the coordinates at P, X, comma, f of X. Okay, now we're going to go out to another point on the graph, and we're going to call that Q, so the PQ graph. And we're going to call the X value, well, we're going to call it X plus a little bit more. Now, if you think about it, when we were in Unit 2, we called that H. We did X and X plus H. In differentials, we don't call it H. We actually call it dx, which means change in X. So we're going to take this X coordinate, add a little change in X, which will push us to the right and give us a coordinate of X plus a little bit more, X plus dx. And so then what that does is our Y value then at Q is nothing more than function evaluated at X plus dx. Okay, so we got that straight. Now here's the cool thing. If you wanted the Y value, the true value on the Y-axis for Q, so you wanted this guy right here, but you couldn't get it. You didn't know it. This curve that Q lies on is just too complicated to deal with, and you're unable to secure the Y value at Q. It turns out you can use calculus and derivatives, which allow us to write equations of tangent lines. You can use the equation of the tangent line at P to get a good approximation to the Y value at Q. It won't be exact. There will be a little bit of error here, but it'll be close. So we can use tangent lines to approximate more complicated curves, and this process is known as differentials. So here's how it works. Well, when you get from P to Q, if you go the horizontal distance between P and Q, we're going to go ahead and call that dx. We kind of already established that earlier. And if you go the vertical distance between P and Q, we're going to call that dy, like delta y, change in y over change in x, delta y over delta x, which is like slope, rise, and run. Okay, so if we want to approximate this Y value at Q, what we can do is, and I want to switch colors here so it really stands out. Oh, what do I have? Let's do this blue pen. I don't know if it works. Do this blue pen. What we can do is we can go out to x plus dx, and we can come up this far. Now this blue distance right here, see that distance is the same height as p. So that y value right there corresponds with f of x. So this height right here is f of x. And then all we have to do is tack on and add a dy to push us from the x-axis up to here, plus a dy, and that is going to give us a rough estimate here. This is going to give us a rough estimate of this, because we're almost up there, not quite, we have a little bit of error. So what did we just do? Well, what we just did is, what we're saying is, the true y value, so f of x plus dx, that's this guy. This is the true y value on the curve at Q. Okay? This true y value, draw a little horizontal line here, is approximately f of x. That's this height. See, this height is f of x. So f of x plus dy. Okay? So the true value is approximately this value, which will get us our rough estimate. Now, we're going to do a little side work here for a minute, because believe it or not, this is not the formula that you're going to see in a book or online. So the side work I'm going to do has to do with getting dy in terms of x. You know how I like my equations all in terms of the same variable. So the side work is this. Do you remember in Unit 2 when we said one of the notations for derivative was dy dx? We used to say if y equaled a function, then the derivative could either be y prime or it could be dy dx. So what I'm going to do is I'm going to set dy dx equal to f prime of x. They mean the same thing. So y or f of x, so dy dx or f prime of x. They both mean the slope of the tangent line of the function. Okay, now what I'm going to do next is I'm going to solve for dy. I'm going to solve for dy by multiplying both sides of my equation by dx. So what that does is it cancels these dx's out, and I'm left with dy equals f prime of x dx. So I'm going to take this right here, and I'm going to replace my dy over here with it. So now I have f of x plus dx, the true y value at Q, is approximately f of x, which is the y value at P, plus f prime of x times dx. So now, what I'm going to do underneath both of these is say what they are. So this guy, again, is the true value, the true y value, on the curve at Q. And this is the y value as per the tangent line. In other words, this right side is going to give me the y value on the tangent line at x, which ends up being my f of x plus my dy. So I'm using the tangent line to approximate the curve. Now, here's the cool part. The smaller your dx, the more accurate your approximation. Think about that. Now, I pushed dx way out to here. Say you had a little dx. I mean, say your dx was only to here. This was x plus dx. Check out what happens when you come up to the tangent line versus the curve. See how there's hardly any error there. This error between here and here is much smaller than the error was out here. So one thing about differentials you'll find is the further you pull away from the point of tangency, the further the bigger your dx is, the less accurate your approximation is. Now watch how cool this is. So this is how we're going to use. Really, all this was to derive this formula, and this is all we really need. When you're working with differentials now, all you need is this. So this is what you memorize, okay? So you can just use this formula now to approximate the square root of 4.6 without a calculator. And here is how you do it. Okay, we don't know the square root of 4.6, but we do know the square root of 4. What you want to do is you kind of want to let your x in this formula right here, you want to let that x be something that you know, okay? So we know, this is how I'm going to start this problem. We know the square root of 4. We can do that in our heads. So we're going to let x equal 4. Now, this means the dx, or the change in x, has to be 0.6, because 4 plus 0.6 is going to give me 4.6. Okay, so in this formula, this is what I've got. I'm going to copy my formula down. So f of x plus dx is approximately f of x plus f prime of x times dx. So what I'm going to do is I'm going to go through this formula. Wherever there's an x, I'm going to replace it with a 4. And wherever there's a dx, I forgot to put equals. Wherever there's a dx, I'm going to put a 0.6. So here we go. So f of 4 plus 0.6 is approximately, see how we're going to do f of 4.6? Is approximately f of 4 plus f prime of 4, and then dx again is times 0.6. Okay, fair enough. Moving on, now we have f of, well, 4 plus 0.6 is 4.6, which is exactly what we want to know. We want to know the square root of 4.6. Okay, now we get into, we need f of 4 and f prime of 4. And this is where we have to sort of go over to the side. This will be our side work on this problem anyway. And we kind of have to define what f of x is. So f of x, to me, in this problem, is the square root function. So f of x is the square root of x. Now, like I said, we know when x is 4, we know what the square root of 4 is. It's 2. So that's fine. But we have to define our function in terms of x. So if f of x is equal to the square root of x, then it'll be very easy to get f of 4. F of 4 will just be the square root of 4, which is 2. So that's what's going to go here, 2. Plus, and now we have to find f prime of 4. Well, in order to find f prime of 4, we have to find f prime of x. So if f of x is equal to the square root of x, which is the same thing as x to the 1/2 power, then f prime of x, by the power rule, is going to be 1/2 x to the negative 1/2, which is the same as 1 over 2 square root of x. We've done that problem many times. 1/2 x to the negative half is the same as 1 all over 2 root x. So then f prime of 4 is 1 over 2 root 4, which is going to be 1/4 when all is said and done. 1/4. Okay, so now bring it back over here. So f prime of 4 is 1/4, and we're multiplying by 0.6. Now, your temptation might be to go throw that in the calculator, but we don't have a calculator, remember, without the use of a calculator. So we'll keep going by hand. F of 4.6 is approximately 2 plus, let's take 0.6 and make it 6/10. So 1/4 times 6/10 is going to reduce to, let's see, these are both divisible by 2, so 2 and 3. So approximately 2 and 3/20. So that's my approximation. It said find a good approximation. 2 and 3/20 is my approximation. Okay, now let me grab another piece of paper. There's more I want to do here, and I've run out of room. I write too big. Okay, so my approximation, let me write this down here. So my approximation of the square root of 4.6 is 2 3/20. Now, to avoid long division here, I am going to just grab a calculator. So if I change 2 3/20 to a decimal, I really just have to take 3 divided by 20. So 3 divided by 20 is 0.15, so 2.15 as a decimal. That's my approximation by differentials to the square root of 4.6. Now, the true value of the square root of 4.6. Let's get that on the calculator. Now we're using the calculator. The square root of 4.6, 2.144, 761,059. Look at how close they are. The error, if I subtract them, so if I take this guy, actually if I take 2.15 minus that answer, my error is 0.005. It's 5 thousandths. That's pretty darn good for not having a calculator on me. And it didn't take terribly long. I wasn't guessing and checking. Now, let's look at, I'm visual. You've known this all along, so let me provide a visual here for you. Here's what we just did. We basically took, so this is x, this is f of x. So let me graph f of x is equal to the square root of x. Okay, we know what that looks like, guys. We know that just kind of arches, right? Like that, okay? What we essentially did is we went to x equals 4. See, let's go back here. See when we let x be 4? Well, what we did, when you identify your x, that's like your p. You basically identified that your p was here, and the tangent line would be drawn there, okay? Boom. That's your x. That's this guy at p, x. Then what we did is we allowed the change in x. So if this is 4, let's say 5 is here, okay, 4 to 5. We went to 4.6, okay, there's 4.6. And what we did is we came and got the tangent line's y value as opposed to the true y value. See, there was just a little bit of error there. The reason our approximation is bigger than the true value is because, as you can see, the tangent line at x equals 4 lies above this curve. So you can see that our blue dot is an overestimate of the true value on the curve. So this y value right here is the 2.15, but the pink right here is the 2.144761059 number. So in a visual, that's what we did. We used the tangent line to approximate this. So, oh, dusty. Did you see that dust fly down off my machine? The last thing I would say about this is, and I'm almost like tempted not to say it, but I feel I owe you all the information. You might say, well then, why don't you just write the equation of the tangent line at P and then just plug 4.6 into it? Well, you can. Like another way to tackle this problem to get the square, remember, the problem was, what's the square root of 4.6 approximately? Well, if you wrote the equation of the tangent line, so write the equation of the tangent line to f of x equals square root of x, at the point 4, 2. Because that's what we know. We know the square root of 4 is 2. Well, we could totally do this. You know how to write the equation of a tangent line. First, you take the derivative, so you would have to take f prime of x, and we know that the derivative of the square root of x by the power rule is 1 over 2 root x, because we did that previously. So then the slope of the tangent line when x is 4 is going to be 1 over 2 root 4, or 1/4. So this is m. So you would have y equals mx plus b. Now to find b, you simply plug your point back in. So y is 2, and x is 4. And so that gives you 2 equals 1 plus b, and so b is actually nice, it's 1. So the equation of the tangent line is 1/4 x plus 1. Now, if you want to find the approximate y value on this curve, or this line, this tangent line, when x is 4.6, you would just plug 4.6 in for x. So y would be 1/4 times 4.6 plus 1, and hopefully, if we take 1/4 times 4.6 plus 1, we get 2. Sorry, you couldn't see that. 1/4 times 4.6 plus 1, you get 2.15, exactly what we got using differentials. The difference is, I think this is a little bit faster. Honestly, I mean, I think it is. Maybe you don't, but this is the alternative to that, is to actually write the whole darn equation of the tangent line, but it means you have to go and get b. So yeah, I mean, it's kind of cool that you can see you get the same answer either way. Shows that the two formulas are working. Okay, so that's differentials. Now, we're probably going to do a little bit more with differentials in another video, so stay tuned for that. This is just a nice little introduction to where this formula comes from and how to use it, how to apply it. Okay, good luck on your mastery. See you next time.